Hi, everybody. It's good to have you here. Do we have any security experts in the room?
I heard you were.
I said exactly the opposite of that, Jeremy. All right. I like this. This is going to be a fun crowd. We're going to have some fun. Cool. So has anybody ever implemented their own kind of like homegrown security algorithms before? Awesome. Yeah. Some renegades, huh? Yeah, engineer tinkerers. So this topic I thought was super interesting. A long time ago, somebody talked to me about like what you could do with the XOR operation, and I was like, oh, that's super cool. Like I'm going to totally try to use that. And I set it on the shelf for a long time, but since then I played around with things like hashing, signing files, and stuff like that. And I totally know enough to be dangerous to myself and others. And I've often been frustrated though, because like, actually implementing like a real security protocol or something like that usually requires a lot of like, digging in, figuring out how stuff works. It's tools designed for hackers, by hackers, and just simple things like, how do you get SSL working in LabVIEW before they had SSL, and then even now that we have SSL, there's not a lot of the features exposed to us LabVIEW users to do some of the things we might want to do with it. But anyways, I'm curious about it. That's the point. So we'll dive in, and I'll talk to you a little bit about what I've explored. This isn't going to be exhaustive, but I wanted to share a little bit of kind of my journey of going from, hey, this is cool, to, oh, okay, there's that consideration, and then eventually realizing that it's a pretty complicated topic when you talk about doing encryption of data. So disclaimer one, I mentioned this, I have no idea what I'm talking about. So this is a group discussion, so if you find that you do know a little bit more about what I'm talking about than what I'm talking about, feel free to chime in. The disclaimer number 2 is you will shoot your eye out. All right, cool. So writing your own encryption will get you into trouble, especially if you're successful. And what I mean by that is once your algorithm, your data signing, encryption scheme, authentication, whatever, once your application becomes successful and it's creating business value for people, somebody's going to want to figure out how to get around that, right? If you have copy protection or you've got IP obfuscation or something like that, there are people in the world that would love to not have to do that work for free and build a business and build the IP. They'd rather just take your useful stuff, because there's another principle. We'll talk about entropy in a little bit, but kind of data kind of tends to want to be open. That's its natural sort of progression. So we can try to keep it from becoming open, but eventually data wants to be open. So if you put it out there, realize that there will be entropy that wants to take advantage of that. But it'll be fun. We'll learn some stuff. We'll and maybe this exercise will introduce some concepts that become really useful once we go out into the world and maybe use some tools designed by security professionals. Okay, I love XKCD comics. So we've got a gentleman over here on the left rattling off some, a highly secure cryptographic cipher technology. And on the right, you can see, for added security, after we encrypt the data stream, we send it through our Navajo code talker. But aren't those just the Navajo words for 0 and 1? Shh. And a lot of systems are actually designed to be obscure. Different algorithms like the ones we'll talk about in here actually have been kept secret by the government. One of the ways in which you can help prevent the information from being deciphered is for people to not know at all how you're doing it, because some of the different attacks rely on getting copies of unencrypted data that got leaked somehow, and then looking at the ciphered data, and if you know the algorithm that was used to do it, you can actually start making guesses at the inputs to the algorithm, like the keys and other parameters, and then you can run that plain text through it and then see, oh, hey, do we get the cipher data stream that we also intercepted? And then once we do that, we know the keys, and then we can decrypt any data in the future and any data generated with it in the past. Okay, but back to the fun stuff. So who knows about the XOR operation? Awesome. So just to show you how much I don't know what I'm talking about, it was only a couple months ago that I realized that the circle with the plus was an XOR. I'm a LabVIEW person, so I always thought it was an upside down A, or maybe it's a V with a little line through it. It's a really cool operator. I actually realized that it was a plus with a circle when I was looking at a checksumming algorithm that was used by a low-level device, and I thought it was just a fancy add symbol. And actually then, upon more reading, I realized it actually is a fancy add symbol, but it's when you add bits, bitwise adding together, you do rollover addition on the bits. So if you have 1 plus 1, that would be 2, but then that rolls over to 0 because it's modulus 2. So that's a modulus 2 addition, XOR. So one of the cool things about XOR is you can use it for encryption and other security stuff. And we'll talk about the XOR Cipher, which is a really cool, really powerful encryption. We'll talk about the implications, but actually understanding some of this stuff is really useful because XOR in encryption is used all over the place. It's extremely performant, and it has some cool properties that make it useful. So I'm going to be talking today about what's called symmetric encryption. And symmetric encryption means that, and again, I'm not a security expert, so take this all with a grain of salt. It basically means you have a key, and that key is used to both lock the data to create a cipher text from a plain text message, and then you use that same key to decipher the data. Okay, so when we look at XOR, one of the things that we notice here, which will come in handy later, is well, let's just start off. XOR of 0 and 0 is 0. That's a useful property that we'll talk about in a minute. And basically, it's true if either inputs are true, but not both. If both inputs are true, then it's a 0. One nice thing about this is that with a uniform, well, based on all the inputs, you can see half of them are true and half of them are false. The outputs, half of them are true and half of them are false. And this ends up being really useful because no information is lost if we're taking information in and getting information out. This will be helpful when we talk about random distributions of keys, for example. So for anybody that prefers to see that in LabVIEW, that's what that looks like. Okay. I always believe you should show LabVIEW code as soon as possible in a presentation if you want to keep a bunch of LabVIEW developers engaged. Okay, so some different XOR attributes. We talked about how A XOR A is 0. And what's interesting is that A XOR B XOR A, because XOR has a commutative property, we can rearrange that as A XOR B. And because we know that A XOR A is 0, that means that we just get B. So A XOR B XOR A is equal to B. Put in a different way, if we have A XOR B and we call that C, I'm going to use C for a cipher text, meaning the encrypted data. If we take that encrypted data, C, and XOR it with A, we'll get B. And why this is useful is if we call A our key and B is our plain text data, we can use A to both lock and unlock our data. So what that meant is it's invertible, and this diagram shows us kind of what that might look like from the perspective of the symmetric encryption that we saw before. So again, this should look pretty familiar. So with the symmetric encryption, what we're going to do is we're going to have a key that we use to lock and unlock the data. M will be our message, and C is the ciphered message. Any questions so far? All right, makes sense. So there's a really cool thing called a one-time pad. And a one-time pad is an unbreakable encryption. And when I say unbreakable, it's even theoretically based on mathematical proofs and first principles. It is unbreakable if the key is truly random, meaning it was created by a random number generator, not just me typing, my secret password. At least it's at least as long as the plain text, which basically means my key needs to have as much random data in it as the data that I'm trying to encrypt. I also can never, ever, ever reuse the key or any part of the key. Otherwise, patterns start to emerge. And also, I have to keep my key completely secret. So how many people are in the room are like, hey, Jim, that looks really easy. Right? And I'm like, oh, that's pretty easy. I could probably do that on a small scale. I have like a file, I can generate a key, I encrypt it, and I keep my key secret. Easy enough. But again, you'll shoot your eye out. All right. So this is kind of what the XOR encryption looks like. Basically, we take a key. Unfortunately, my mouse doesn't work here. We take a key and we XOR it with some plain text. And I created a key of the same length called Jim's secret, and I XORed it with the plain text. And then I get a ciphertext out. And those boxes aren't actually repeating boxes. Those are just non-printable characters. But then we can see the deciphered text is the same thing that we had initially, which is cool. But the Jim secret is really a problem. It's not truly random data. And so if the key isn't truly random, patterns can be seen and exploited by attackers. And basically they use what's called just like probability distribution. So the English language, for example, there's a certain probability of characters. The other thing too is like the space character is used a lot, and null characters are used a lot. And so what will happen is if there's an analysis done of basically plugging in just the English language characters, you can actually start to decipher. If you start to get enough data that's encrypted with my password, you'll start to see, that there were a lot of H's in there, a couple E's. Now this is relatively small, so I'm not sure how big of a deal that would be, but for larger ones it will be an issue. So if we look at the plain text frequency distribution, we can see that those bytes have 256 possible values, but mine are really just all kind of clustered here. Again, this isn't a very large data set, but you can definitely see that like I'm not using half the space in the total space for a key. And so that was the plain text distribution. This is the key frequency distribution. And if I look at the cipher, it's also not random. And what ends up happening is, well, I'll get to that later. So attackers look for frequency distributions and other patterns in the ciphertext. So we said that a one-time pad needs to be truly random. And what truly random means and why it's important, essentially, if I have a key and the key is truly random, when I XOR it with the message, the cipher will appear truly random. And basically what ends up happening is that the data output will have as many possible combinations as there were in generating the key, and it will truly be indecipherable. The problem really comes in the definition of what it means to be truly random. And what's that?
I'm agreeing with you.
Yeah, and so really what it means to be truly random, and we talked about that, is that some physical process like rolling the dice, flipping the coin, or using like noise on like a semiconductor, or sometimes they use like several different harmonic oscillator crystals and then do some kind of combination of math on them to create something that's truly random. If it's just a pure software-based randomization algorithm, and there are some functions that approximate randomness, it will be possible to see patterns because it won't be truly random. And some of the security flaws that people discover in algorithms is basically they figure out ways in which the random number generators aren't actually random. And we'll talk a little bit more about that in a second. So here I'm using a random string, and this isn't a true random number generator string. Basically, under the hood, I'll show you what I'm doing here. Oh, that was that one. So inside of my random number generator, can everybody kind of see that okay? Okay, cool. Basically, it's just getting a number from 0 to 255 using the OpenG function. I was actually testing to see if it was working the same way. But effectively, I'm just doing a little math using LabVIEW's roll of the dice here between 0 and 1, and I'm scaling it up to 0 to 255.
Is that proven to be totally random?
NI's random? No. No, it's not a true random number generator. Date time seeded, yeah. So don't rely on this for real cryptography. What will end up happening too is if somebody were to do some sort of plain text attack, they have some data that got leaked and they knew the ciphertext of it, and they knew the algorithm that I was using, they could essentially figure out under the hood what the seed value of the random number generator was, which actually then lets them sort of back reverse engineer all the previous data that has been encrypted by the algorithm, and they can also forward engineer basically how to decipher with that. I don't know all the details of how they do that. There's some pretty heavy math under the hood for some of these automated decryption algorithms. Okay. So what we'll see here, the difference, I just took some lorem ipsum text and plugged it in and looked at the plain text frequency distribution, and we can see that it's totally not random. And here, I just generated a random key of the same length as the input data. You can see this looks very random. And if we look at the cipher frequency distribution, it's completely spread out, and there's really no way to decipher any information from this unless you have the original plain text information and were to do some kind of dictionary attack on it. So we mentioned a true random number generator is a device that generates random numbers from a physical process and not simply a computer program. Okay, so the last three items on the list we talked about, the key needs to be at least as long as the plain text, and no part of the key can ever be reused, and needs to be kept completely secret. So for very large data sets, for example, the streaming of data, it's impractical to securely transmit a secret key that is as long as the data. And so one approach that people have tried is they will generate a huge random key they'll put it on a CD-ROM, and somebody, flies it in a briefcase with, handcuff on it, and then they take it to the other party that's going to use it, and then over some transmission line, like a telegraph line or whatever, the sender will be using the copy of that CD with that key, and then they'll be encrypting data as it goes by. But in order to not reuse the key or any part of the key, they're going to run out eventually. So you essentially have like kind of these two streams that have to happen. You're transmitting your encrypted data, but then you need to be able to securely transmit your key as well, which ends up being pretty tough. And there were thoughts that even during the Cold War, the little red emergency phone between, I think, Russia and the United States, like actually had one of these kind of secret keys, really long secret keys that was used to encrypt the data between those two points. Okay, so in terms of practical approaches, basically what scientists and engineers are going for is something that's good enough. And so essentially, good enough encryption basically means that the time it takes to break the encryption is longer than the time the data needs to be protected. And also too, they're going for algorithms that once you do break the encryption, hopefully you can't go back and break other things that were previously encrypted. You can only break new things encrypted with that algorithm. And so a lot of the work in developing encryption algorithms is done in looking for random number generators. And we'll talk in the concept of streams, why that's an area where people are doing a lot of work. But effectively, if you have both parties know an algorithm for generating the same sequence of numbers that look purely random to an observer, then you don't actually have to transmit the random data. You just maybe transmit securely a little bit of kind of starting off information that seeds the random number generators. Then the random number generators are basically outputting the same key in parallel to the data coming in and the data coming out. So a lot of work is spent in making sure that those random number streams actually are producing true random numbers and looking at the probability distributions. Some of the exploits are when they discover, oh, you know what, there's like the second bit of the bit stream has a chance of like 2 chances in a million rather than 1 chance in a million. And then the way around that is to actually, they throw away the first 256 bits, and they implement an improvement to the protocol. And a lot of work goes into determining how to break the algorithms. So people keep a catalog of the different ways and routines in which people can break the algorithms, but that doesn't mean that there's not a more efficient way to break the algorithm, and there's actually no way to totally know what the fastest way to break an algorithm is. So it's constantly like this race between people developing new algorithms and folks trying to break them. And you can also imagine too that the longer they keep the algorithm secret, the harder it is to break them. However, one of the good rules of thumb for people in industry especially who are using some form of encryption is to use an open standard. And what an open standard means is everybody knows the algorithm. Now the algorithm is one of the secrets, but if it's really, really good and everybody's participating and finding the weaknesses in it, then you have a much better idea of exactly what are the exploits and how much time would it take using today's computing resources to break that cipher. And then you can make good business decisions around, well, this confidential information only needs to be kept confidential for the next 5 years, so this algorithm is good enough. Okay. So, pseudo-random number generators generate a sequence of numbers that appear random but have a deterministic sequence given a seed input. And one thing when I was researching this that I thought was pretty interesting is they did you can do an experiment where you have like a computer random number generator flipping a light switch, and it's turning the lights on and off, and then in the other room you have a person like just trying to do it random, up, down, 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 up, and just like totally random, right? And what'll happen is both of them, if you're just looking at them, they look totally random. But what ends up happening is, for whatever reason, humans have this characteristic of kind of picking certain patterns more frequently. Like I might, for whatever reason, based on who I am, like up, up, up. And some other person likes, down, 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 down a lot. And somewhere in the randomness, that one pattern will pop out. Even more, so if you do that with a person, what you will find is over time, you will have half zeros and half ones. You'll have a very even distribution between 0 and 1, but the sequences will be non-random. And so then if you know that this one sequence appears more often, you can then subject it to a dictionary attack where, like in the English language, that, the certain letter appears at a certain frequency. It's going to hit that zone more frequently that has like the 4 ons, and it'll start to like rise above the noise floor after a long period of time. And then once you know that, then you can start knowing the key, and then you can get more information, and then it kind of snowballs. I thought that was really interesting, and so that's why there's so much work on these random number generators and making sure that they never have any repeating patterns in them. One thing that kind of solves that problem is if you can come up with an algorithm that can generate random numbers that are essentially seeded and have a deterministic reproducible sequence given a certain kind of set of input values. And so this function, essentially, as you iterate on the function, it outputs data that looks very, very random, so somebody intercepting it will not know that there's information in it. And both sides, both the sender and the receiver, can be generating this sequence of random numbers in the exact same order. So LabVIEW has a pseudo-random number generator that I'll use in this example, which is Gaussian white noise. And I already mentioned that. And we can use that to basically generate streams of random numbers indefinitely. It's kind of cool. Okay, so what I wanted to show here in this example is that if we have our random number generator and both loops are using the same seed, then what will happen is that both the upper loop and the lower loop have the exact same waveforms of random numbers. And so what then becomes important is not so much transmitting the entire CD-ROM full of random numbers, but just transmitting a seed securely, a very small piece of information. And if that small piece of information can be transmitted securely, then both sides can start that operation. All right. So with key streaming, we have some initialization variable. This is a general term for these types of stream ciphers that are used to set up the key streamer. And then the key streamer iteratively starts streaming out keys, and these guys are outputting the same keys. And then the messages are being encoded. The ciphertext is here, and then they get decoded with the same key and get output. Any questions so far?
So
Comments?
Message, and like if the receiver doesn't get all the messages, if they miss the first message, then the whole thing is.
Yeah, they need to know what index the message is for sure.
I think it's nice to talk about this and how you transfer that seed.
How do you transfer what?
The seed, like how you share the seed
Ah.
with each other without.
Yeah, that becomes sort of the next problem, and then the next problem, and then yeah. So the how do you do this ends up being this huge source of problems potentially, and then also too the pseudo-random number generator. If there is any kind of patterns that can be detected, it's not truly random, then this can get cracked. If you then figure that out, you can figure out, oh, we know the statefulness of this thing. If you then know the statefulness that was used to do this, you can start like reverse engineering like all the previous states of past messages sent with this algorithm, in addition to all future messages sent with this algorithm. And so the XOR operation is referred to as a cipher. And all of the kind of the business of how we put these things together in pseudo-random number generation and initialization is referred to as the modes of operation. There's some interesting algorithms as well that can take part of the outgoing cipher, and they'll take like a byte of the cipher and XOR it with the message coming in before encrypting it. And so what ends up happening is the cipher actually starts to have a dependency on the input stream in addition to the seed, which then makes it even harder to kind of get information. And you can start doing that like all kinds of crazy times. In a little bit I'll tell you about one of the newer algorithms that they came up with. So here's a streaming example, and we'll talk about practical approaches. Yeah, I've got it down further, I think. So basically what's happening here is I'm generating 8 bits. And
But he's having his private zoom in there.
oh yeah, zoom in. Here, let me put that down real quick. Watch your eyes, Matt. Okay, so what I'm doing here is basically generating a random byte. So I'm asking LabVIEW's Gaussian white noise generator to give me 8 floating point numbers, and these basically have, they're either going to be above positive or negative. Some of the inputs here basically just affect the amplitude, the distribution of the data. And so I'm just going to do a quick test, greater than or equal to 0. Now, what's probably going to happen here too is it might have a slightly greater chance of being greater than 0 than less than 0, and I should probably be flip-flopping it between greater than or equal to 0 and less than or equal. I don't know. I'm not an expert. I'm just going to shoot myself in the eye here. But so basically, then what I do is I take that, and you can see that I've seeded it here, and I'm going to take this data stream, convert it to an array of bytes, and then one byte at a time, I'm going to stick it into this channel wire. I thought it'd be cool to use a channel wire so I didn't have to mess with queues and other things. And then, as you can see, there is the tricky business of how do I get my seed secretly to the receiver. And what I've chosen to do is to essentially have a shared secret between the sender and the receiver, and then I encrypt the seed, and then I decrypt it over here and use it. And this also, again, isn't very secure. If I were to send another seed this way, then I'd be using the same secret 2 times. But it just kind of to show the point of, there's a protocol for initializing the system securely. And that's really a huge kind of rabbit hole you can go down as well. I showed a streaming example. And there's a lot of interesting places sort of I thought we might be able to go with the presentation. You could talk about like the different algorithms that are used for doing pseudo-random number generators. I'll just mention like there's interesting things that people do with like adding shift registers in here, and then having an algorithm that both the sender and the receiver know about, that are sort of like XORing the output in cipher data with like the next packet. And so it's an algorithm that actually sort of adds randomness that's in some ways basically seeded by the plain text input data, if that makes sense. So the output, essentially the cipher, depends on the plain text as well. So there's a lot of interesting areas there. I think the industry standard one is a really weird looking sort of feedback register system where, they have a shift register where they, this one has like 64 bits, and then this one has like, 83, and then they take the output of this and feed it into this one, and then they take the third bit off of this one and feed it back into here, and the XOR these, and it just happens, somebody figured out that routine outputs a very, very random non-recurring bit stream, and then a lot of energy is put into, well, what are the weaknesses of that? Some of these things are also patented. Different pseudo-random number generator schemes are patented, which means then you pay a license fee if you want to implement that encryption algorithm, which I guess is good because a lot of money and research goes into developing these things. Okay, so one-time pad. It started out pretty simple. It's pretty easy to do one time. But once you start streaming or have very large data sets, it gets hard. And seriously, if you break any of these rules, the encryption will be broken. It's just a matter of time. The more rules you break, the easier it is to break the encryption. It's easy to break the rules without knowing. I'm sure in all the code I've shown you, I've broken probably every rule. But still, have fun, be safe, enjoy the learning process. Thanks, everybody.